in the polymer age, which means that many of the materials around us are made from synthetic polymers derived from petroleum. Now, these materials provide us with many desirable properties and uses, but they do come at a cost, and that is that they degrade very slowly. So we have a challenge with waste management. Today with me is Dr. Alexander Golberg from Tel Aviv University, and he has potentially one of the solutions. These are bioplastics, and bioplastics made from a very unusual source. Alex, thank you for coming. Maybe we can kick off with you telling me something about bioplastics and your perhaps unique way to make them.
Sure. So first of all, let's decide what bioplastics is. So bioplastics is a mixture of polymers, and today most of them are derived from synthetic sources. So if there are big families of different bioplastics used with different properties. Some of them are transparent, some of them are colored, some of them are thermostable, but the idea is that all of them are coming from the renewable sources such as biomass. So what we are focusing on the very specific question on how actually we are making this biomass and how we are making those polymers. And the idea behind our project is that we do not want to use no arable land and no drinking water for the production of those polymers. So how we do this? We use seaweeds. We grow seaweeds as a raw material, as the biomass, and then it took us some time to find organisms which are able to eat those seaweeds and to produce polymers, which are called the polyhydroalkanolates or PHAs.
So the source of energy are seaweeds. They're converting sunlight into biomass. That biomass then is fed through to bacteria, which can transform those chemicals into useful plastics, useful polymers. That's the correct understanding of it. And I suppose one of the largest additional benefits to this is that we don't have to sacrifice any land or water, indeed, as a resource which could be spent on food production, for example.
Yes, so the debate about food over fuel is known for years now, since the biofuel started to penetrate the market. The idea behind the biofuel was that we can use biomass to make fuel instead of petroleum fuel and burn it. And then once these started to get into the high-scale production or large-scale production, we found immediately that there is an immediate impact on the food prices. And we got food riots, and there's a lot of noise around the world of how exactly we're going to produce biofuels today. So are we going to take a hectare of land which are currently used to the production of food and use it for the production of fuels? So here we come in exactly to the same question. So if we want to make materials such as plastics or polymers, which everybody needs today or uses, are we going to sacrifice some land which is used for food? Or are we going to convert new land, which leads to the deforestation? So actually we're going to cut trees to put new plantations to produce polymers for the plastics.
But ultimately, surely then it's going to come down, unfortunately, to cost. What is the source of our biological matter which is going to be used in the formation of these bioplastics? It's going to be what's the cheapest. How does the use of seaweed compare with other potential uses?
So the cost is not exactly what the cheapest, but it's also going to be what's the most sustainable, because at the end we will pay for everything. And I think that today seaweeds already can compete with other biological sources.
And are you convinced with a general public recognition about the cost of sustainability? Do you believe, are we doing enough as a society to understand what are the costs involved with sustainability?
So I think that we're on the track, and we see this in the recent years, that actually the actual cost of sustainability appears in more and more places, such as fuel, materials, and even food.
Okay, so tell me a bit more about the microorganisms which are involved in this conversion of the biomass into the biopolymer.
So thank you for the excellent question. And initially you mentioned we're using bacteria. So exactly these days we're not using bacteria but archaea, which are archaebacterium, which are very specific types of microorganisms, and they're different from regular bacteria. And in addition to their structural differences, they also are halophytic microorganisms, which means that they're able to live in the very salty environment. So it can be a Dead Sea, it can be a solar ponds in Spain, for example. So the one we're using, this archaebacterium, what it's able to stay for live in the environments which go to 170 grams per liter of salt, which is a very salty soup, let's say. So they also are able to eat many types of food. So it's not only sugars, but they also eat polymers, short polymers, oligosugars, lipids, and so forth. And eating all these, they grow and they produce the PHA at the same time. And we can get up to 60–70% of their biomass as the PHA.
As a single polymer?
PHAs are usually a mixture, so we're calling a PHA, it's a polyhydroalkanolates, which means that there is a mixture of polymers. The major one we are producing is PHB, polyhydrobutyrates. It's only one, but it's always a mixture of things coming together.
And the separation of these mixture of polymers and the rest, is that a complicated, energy-intensive task, or is it rather simple?
So these days this is a complicated task because the organisms are small, so we're talking about micro-sized organisms, so we need to separate them from water or the medium where they grow, and in addition to this we need to separate PHAs from the inside. So that's an actual challenge, and there are multiple processes we're looking into how to do that.
Well, I'm presuming that you have to use a centrifuge.
It's one of the solutions. We can use also different types of water extraction techniques. We can use advanced techniques such as post-electric fields, for example, so my laboratory is working on, which can provide the green chemistry-based approach for their separation.
And, sorry, remind me, the polymers coming out, are they thermoplastic? Are you able then to heat it up, melt it down, form other different types of materials, thin films, thicker objects, or how does that work? What's the physics?
So we're talking about polyesters, and their properties depend ultimately on their length chain and their exact composition. So today PHAs are thought to be composites of the thermostable plastic, so which means that over time we will need to extract them, purify them, separate them by size, and then make a composite materials where they will play a certain role. So they provide mechanical stability, thermal stability. And
so composites, they don't need to be used in their pure form. You can mix it with other sources of polymers, let's say.
Yes, like any other polymers which are used today in the plastics. It's very rare that you use a single source.
So a future could potentially be not a binary choice between synthetic and bio, but it could be that we're going into mixtures of these.
It could be, and it's already there, because the question is about biodegradability. And so the question is how fast these polymers or those plastic materials are decomposed.
Right.
So if you build it away in the composite material in the way that it has a biological source and synthetic source, and both of them are decomposing faster than each one of them separately. So that's the win-win situation.
But is it then possible that the biological sourced polymer will decompose rapidly, leaving the synthetic microplasts maybe in the environment?
Could be oppositely too. So because we know about the biologically derived polymers today, which are almost not degradable. So it takes them days and hours and even years to be decomposed, especially in the marine environment. So not everything which is biologically sourced is rapidly biodegradable.
Yes. And what do we understand about plastics, the bioplastics which you're generating, for example? What do we understand about the mechanisms of their decomposition and how that goes through the environment?
So PHAs are actually interesting materials, and we harvest them from the marine organisms, which already could have some ideas that they will be decomposed more rapidly in the marine environment than others. So what we know today from literature is that we lose about 10 to 12% in 400 days of those polymers if they're decomposed in the marine environment, which is the most challenging source. And this is actually doing very well in comparison to other biologically derived polymers in this specific environment.
So okay, and then ultimately though, but is there evidence that they accumulate afterwards in, I don't know, in animal species living in our oceans and seas, or is that just too far down the line? We don't quite understand all the finalities of where they end up. So
I think their life cycle we still don't understand completely. So we do know that they decompose in orders of magnitude faster than the regular petroleum-derived plastics these days, which take hundreds of years to be decomposed. But to tell exactly what will happen to them in the marine environment, for example, if we start to produce them in the volumes we are using synthetic plastics these days, I think it's too early to decide about.
So if I'm thinking about the production of polymer molecules by living organisms, microorganisms, I'm thinking about enzymes that are doing specific jobs, and then if they've got enzymes making these chemical adjustments and transitions, then surely we can look into the genetic code of these organisms and we could modify them such that we could produce whatever we wanted. Is that the case?
So this is one of the cases, and this is not the case we pursue. So I think that today we know very little about the natural diversity of the organisms and the natural diversity of those polymers to come to use those advanced tools you just mentioned. So our approach these days is to go and look for new organisms with new polymers, with new enzymes, which will produce properties we're actually looking for. So somewhere downstream the road probably we will go into what you mentioned. One of the tools is synthetic biology, where I can take the specific enzymes or specific pathways inside and manipulate them. But I think to get there we first need to understand what we have, and probably we'll have it in a natural way, that there is a certain microorganism which actually produces polymers which we need to replace a lot of polymers we make from plastics.
So that means you have to carefully observe an entire population of these microorganisms, look very carefully at the polymers they're producing, and then try to isolate a particular strain, and then look to culture those to achieve a sort of a purity of a particular polymer with a particular property that might be desirable.
Exactly, and this is very similar to what you have today with the regular polymers used in plastics. So you look for the polyesters or polypropylene. This is not a single polymer, these are libraries of many polymers with specific numbers, with the specific properties they're built of to use in the composite materials. So what we hope to do, we hope to create those libraries from the marine organisms. So we want to have multiple polymers with different properties which we can actually combine and make plastics.
Compare for me, Alex, the properties of synthetic polymers and the biopolymers which you're interested in producing.
So these days we mostly looked into the thermal properties and mechanical properties, and what we can say that we do need to make blends to achieve the properties which are close to the ones used with the synthetic ones. So we use not only PHAs, but we also do different mixtures of PHA and PLA, for example, polylactic acid, to provide the certain flexibility. So if you want to have a very, very robust material, you will use less PLA. If you want to have a very, very smooth material, a plastic material, you'll probably need more PLA. But these are the pathway we're looking into.
So if you get those mixtures, those proportions correct, you're claiming that they can easily reproduce the sort of important properties that we can achieve with synthetic polymers.
So that's the direction, and that's what we're targeting to. So we want to have a library of different biological polymers, where under different blends we can actually go and replace by one plastics polymers we are using these days.
What's the biggest current challenge with that? I mean, is there a particular property which we're still missing? Is there still another, is there a holy grail in terms of properties which we cannot yet reproduce that we really would like to?
So this is a very interesting question. I will tell you that we actually do not know yet the DNA of plastics. So we don't know actually why plastic materials behave the way they behave exactly. So we definitely, the industry knows a lot. There is 100 years of research done in the plastic materials, and a lot of blends are available. But to go and to make a rational plastic design, I think it will be far-stretched. So,
because I ask that because one of the things I read about is that a problem with or a challenge for bioplastics are linked with its porosity to gases and fluids, water, humidity, for example, which could prevent their wide-scale use in many single-use plastics. I'm thinking mainly food packaging, and I'm thinking very much as well in medicinal uses. Is that the case?
I don't think so. I just really think that we are still not there to come up with those conclusions, because the bioplastic research, if you look into how much years and efforts was put into this, is just in its infancy. So given the time and effort invested, I have no doubt that those polymers will cope with all those problems you just mentioned in terms of gas permeability, liquid permeability, biocompatibility, and so forth. So, for example, the advantage of using archaea, or the archaebacterium we are using for the production of PHAs in this case, is that they don't have endotoxins. So if you do the same exactly polymer in bacteria, you will also need to get rid of endotoxins, and then the medicinal usage could be challenging. In archaea, there are no endotoxins per definition inside them. So this is just the example of how choosing a different organism leads you to the same polymers, but without complexities involved.
So you're painting for me an optimistic and I think a very refreshing picture of what could be in the future regarding these materials. Ultimately, however, we have to talk volume, we have to talk the capacity. Is it reasonable that we can, using these technologies that you're developing, for example, will we be able to produce at high volume, high throughput, low cost these materials?
So let's take the example of polylactic acid. So polylactic acid is the synthesized polymer, but it's initially produced with the fermentation, so biological origin. And this polymer already takes about 1% of the global plastic production, which is a significant one for the biologically derived material. So I think that given the development of processes which will enable low-cost production of those polymers, it's possible to achieve the high volumes.
Okay, so we've got high volume, we've got good properties. What's the future? Where do you see us? Where does this take us?
So the future is the timing. So if we look into the production of how much time it took us to get where we are today with the plastic materials, it's about 100 years. So, and we actually cannot afford this another 100 years to develop the biologically degraded or biologically derived plastics. So we need to condense this to 5 or 10 years, and about 10 years we'll be able to replace the major part of plastics with the biologically derived and biologically degraded materials. So that's the challenge.
And who's going to drive that? Is this going to be a question for companies themselves who are currently interested in the production of polymers driving that? Is it going to be ultimately down to us consumers? Is it going to be legislation from governments? What's your view on that? So
we need this triangle of consumers, legislation and big companies. So without these three, it's impossible to achieve this goal, because we see this on the multiple example of different environmentally friendly products, let's call them this way, that without proper legislation, it's almost impossible to put them into market. So look into the example of biofuels. Now, we do need a legislation which will actually drive the big companies to replace their currently used polymers with biologically derived. Now, both legislators and big companies are influenced by the customers, because the government serves the people, and if people come and say that we want those materials, so the legislation will follow very, very fast. And in the same way, the companies will follow, because they still want to sell the products to the people who decide what they buy.
Dr. Golberg, I want to thank you very much for your time and that you've devoted to us. I want to thank you for the fact that you've come from such a large distance to come to us and speak with us. I want to wish you well with your research efforts and with your intention to make a big innovation regarding bioplastics. And as a little sort of gift from us, I have this for you.